You know when you're driving past a giant factory or a power plant and you see those huge structures with steam pouring out the top? Well, they're not just for looks. They're actually the hidden giants of industry, working around the clock to keep our modern world running. Today, we're going to pull back the curtain on one of the most common types, the induced draft cooling tower. All right, so here's our game plan. First, we'll tackle the big problem these towers are built to solve, all that industrial heat. Then we're going to take a peek inside the tower itself, piece by piece. After that, we'll follow a drop of water on its journey, dig into the cool science of, well, cooling, and finally see how engineers measure the incredible power of these machines. Okay, so let's start with the fundamental challenge here. Pretty much every industrial process, whether it's making electricity or manufacturing chemicals, creates a ton of a byproduct you can't just toss out. Heat. Massive, massive amounts of it. And that leads to a really critical question. We're not talking about a little bit of warmth here. This is an enormous amount of energy that has to go somewhere, safely, efficiently, and all day, every day. If you don't get rid of it, the whole plant could literally grind to a halt. So, how do they do it? Well, the answer is this amazing piece of engineering, the cooling tower. At its core, it's just a giant heat exchanger. But to really get how it works, we've got to know its parts. So let's break down the anatomy of this heat giant. Right at the very top, you've got the fan assembly. You can think of this as the lungs of the entire tower. This massive fan is what pulls or induces a huge draft of air up through the whole structure. And its position right at the top is the key giveaway that this is an induced draft tower. That's what the name means. It's pulling air in and up. Okay, next up is the water distribution system. Hot water comes in from the plant and gets pumped into this whole network of pipes. These pipes end in a bunch of nozzles, and their job is super important. They spray that hot water in a fine, even mist over the entire area of the fills that sit right below them. And now we get to the fills, or what some people call packing. This is the absolute heart of the whole operation. It's basically a dense grid of material that's designed for one single purpose, to create a gigantic surface area. It forces the falling water to spread out into a super thin film, which maximizes the contact time with the air being pulled up. This right here is where the real magic of heat exchange happens. Just above the fills, there's this really clever part called the drift eliminator. See, as all that air rushes upwards, it can carry tiny water droplets with it. This zigzag barrier makes the air change direction really fast. The air can make the turn, but the heavier water droplets can't. They smack into the surface and fall back down. It's a simple trick that saves a ton of water. On the sides, where all the air comes in, you'll see these things called louvers. They look pretty simple, but they're total multitaskers. They guide the air into the tower smoothly. They block sunlight, which stops algae from growing. They help cut down on the noise of the falling water, and they keep junk like leaves and debris from getting sucked inside. And finally, way down at the bottom, you have the cold water basin. And it's exactly what it sounds like. It's a big pool that collects all that now chilled water after it's trickled down through the fills. From here, a pump just sends it right back to the plant to soak up more heat, and the whole cycle starts over again. Okay, so we've met all the players. Now let's put them all in motion and see how they work together in this non-stop dynamic process. Let's follow a single drop of water on its journey through the cooling cycle. So picture this. The hot water arrives at the top, fresh from absorbing heat from the plant's machinery. It gets sprayed down onto those fills. At the exact same time, that giant fan is pulling cool, dry air in through the louvers on the side. This air flows right through the fills, mixing with the hot water. The heat literally jumps from the water to the air, which then becomes warm and full of moisture. That warm, damp air gets shot out the top, and the now cool water falls into the basin, ready for another trip back to the plant. It's just a continuous loop. And this diagram shows us something really important about the design. It's called cross-flow. See what's happening? The water is falling straight down, vertically. But the air is being pulled horizontally, across it. Their paths literally cross each other, and that's why these are often called cross-flow cooling towers. So we get how it works mechanically, but what's the actual physics going on here? To really understand that, we need to quickly talk about two different kinds of heat. Okay, on one side you have sensible heat. This is the heat you can actually sense or feel with a thermometer. When you add or take away sensible heat, you change a substance's temperature, but it stays in the same state, like heating up cold water to make it hot water. It's still liquid. Then you have latent heat. This is kind of like hidden energy that's needed to change a substance's phase, like boiling water until it turns into steam.
The wild part is, during that phase change, the temperature actually stays the same.
So here's the key takeaway. In the cooling tower, the hot water comes in as a liquid and it leaves as a liquid. It's not being boiled into steam. Its phase doesn't change at all. All that's happening is its temperature is dropping. And what does that mean? It means the cooling tower's main job is to remove sensible heat from the water.
Right, so if these towers are getting rid of these just massive amounts of sensible heat, how do engineers even measure that? As you'd probably guess, they've got a standard unit for a machine's cooling capacity.
And they do. It's called the ton of refrigeration, or just TR for short. It's the industry standard unit of power that tells you exactly how much heat a cooling tower is capable of yanking out of the water that flows through it. So what does that really mean in terms of energy? Well, 1 ton of refrigeration is officially defined as the power to remove 3,024 kilocalories of heat every single hour. And to put that number into perspective, even a pretty modest industrial cooling tower might be rated at 100 TR. That means it's powerful enough to pull over 300,000 kilocalories of waste heat out of that water every single hour. The amount of energy being managed is just absolutely staggering. So, the next time you see one of those giant steaming towers on the horizon, you'll know exactly what's happening inside. It really makes you think, right? Behind the screen you're watching this on, the car you drive, the electricity in your home, there's this immense invisible process of heat removal that's making it all possible.